Hi, this is Mr. Campagna. Today we're going to take an opportunity to look at some emission spectra from various elements to better understand the relationship between energy level and spectral emissions. So let's go back to our analogy from earlier. Our friend Diego is finally going to college. He's very excited to be going to a dorm room, but the university has an odd way of determining how much a student should pay for the room that they're going to be staying in. Now, the way that they're doing it is that students that want to live on lower floors so they don't have to get so tired carrying their things, the college has ruled that you pay money to move down on a lower floor and you earn money to move up to a higher floor. Each floor has a dollar amount, and this was the formula that we were using to determine that. The formula that we used was money earned or spent equals the dollar amount of the final floor minus the dollar amount of the initial floor. So you notice that there were two students that we've done the calculations on already. It was Angel and Diana. Angel went from floor 1 to floor 2, thereby earning money because it went from an expensive floor to a less expensive floor. And Diana went from floor 3 down to floor 2, so she's going to be paying an additional amount because she's moving to a more expensive floor. So how does this analogy compare to what's going on with energy levels within an atom? Well, discrete spots that Niels Bohr referred to as energy levels. He labeled them 1, 2, 3, and so on. Electrons can't be between the two levels, just like people can't live between the two floors in a college dorm. When electrons go down, energy levels emit energy, whereas when electrons go up an energy level, they will absorb it. And to bring this back to our analogy, as students move from high levels down to low levels, they pay money. And as students move from low levels to higher levels, they gain money. So if we were to take a glass tube filled with hydrogen gas and then run a high current through it, it would emit radiation. And in this case, the radiation would be primarily light of very specific wavelengths. In fact, you can see here that as the light passed through the slit here and entered into our prism, it can then be converted into a series of these emission lines. So maybe it looks like a spooky blue color, but what actually is happening is you have a violet, a blue green, and a red, all emanating light, and this is tied directly to those electrons jumping up and more particularly falling back down to a lower energy state, because that's where the emission comes from. When the energy state goes from high to low, we're paying that extra energy off in the form of radiation, and in this case, light of a specific wavelength. So let's take another look at the hydrogen emission spectrum. Remember, all wavelengths are measured in nanometers or nanometers. Here we have a lavender colored one at 410, a blue one at 434, a green one at 486, and then a red one at 656. Now, really, all you're looking at here is electrons going from higher levels down to lower ones. So let's say we energize the hydrogen. Some of the electrons jumped up to energy level 3 and eventually fell down to level 2. On their way down, that is where they emitted their light as photons. And in this case, it would be red photons. And these other guys right here, 410, 434, and 486, are just from higher levels falling back down. Now, every element has its own specific wavelength that it will emit energy at. For example, this is what hydrogen looks like. Helium, lithium, beryllium. It's like a fingerprint for each element. And these spectral fingerprints are all dictated by the energy levels of the electrons within them. And just to recap, electrons, when they go down energy levels, will emit energy, and that energy can be seen as an emission spectrum, where electrons going up energy levels will absorb energy. I hope this was helpful. Thanks for watching.